Okay, I'm screen sharing now. Nothing was due today. Wow. We have a pre-lecture due on Wednesday, and that will be the last lab day for the Wednesday lab. The last lab for the Friday lab will be this Friday. Last pre-lecture will be on Monday, and no labs the following week. So one more week of lab. I've got a few grade increasing opportunities. If you send me a course evaluation receipt, you can either do the hit the button that says notify instructor, and I will get an email, and I will email you back. That's probably within about 24 hours. Yes. And fall's supposed to be normal. I was talking to somebody on Sunday who's teaching at whichever universities in Salem, Oregon. And they haven't had a single in-person class all year, which is sad. And they were sort of talking about going back to something like we're doing in the fall. I was like, gee, we've been doing that all year. But or you can email me and say you did it. Send me the thing saying you did it. I will give you 5 points on the final exam. There's also a practice final that's already been posted to BB Learn. If you complete that, you can turn it in with your final or email it to me with your final, and I will give you 10 points on the final exam for completing that. It's a much longer version of every problem I could possibly put on the final exam. Yes, it's going to be both. And it will be at the same time, because I don't want to even mess around with the whole idea of putting something at an alternative time during final exam week, because it's the exam schedule is pretty tight as it is. So I will put up with it once. This is a small enough class. I think I can do it. My other classes are even smaller. Let's see. I think somebody was chatting at me. Nope. Okay. Homework 12 has 21 bonus points on it if you want to help pull up your homework average. And I will take 1 week worth of late lab for credit. It has to go through me, because I've had people try to turn in a late lab to me and to lab TA number 1 and to lab TA number 2. So late labs have to go through me. Just email it to me. If it's a multi-week lab, I'm only going to give you maximum 1 week's lab worth of credit for it, okay? So like if you, maybe like lab 4, you did 2 activities and not the third, I will take the third activity. So that should help you out if you had to miss lab for any reason that was unexcused. Yeah, and I may have time for the J word. Really excited about this, but it's coming up more and more in advanced microelectronics, nanotechnology. When we get down to 1 nanometer, how are we going to make these transistors even smaller? And the only thing that people have been able to come up with here, they're talking about the J word again. A J word is a junction FET, and it's basically based off of PN junctions instead of the MOS capacitor. Kind of works the same way, except you have to put voltage to it to keep it from shorting out and blowing up. The really fun part about JFETs, you forget to turn on the gate before you turn on everything else. Yes, they blow up. You have to convince the audio logic guys, no, really, I need that power supply to come up before anything else. You got to delay the battery coming up, and they're yelling at you. But we may talk a little bit about those and start the final exam review earlier. So MOS has really been ruling the world since microelectronic world, pretty much dominating since the late 80s. We had to go to FinFETs to get for like maybe the past 5 years. And this is what we've been using for the past 5 years. They still work like MOSFETs. Those MOSFET curves, everything you've learned about MOSFETs still applies. What's on the horizon in the next 6 months is these nanowires, which are actually turned into nano sheets, a little bit wider version of nanowires. And this is what they're doing to get down to 1 and 2 nanometers. And we'll talk more about that and why it works in EE280 in the fall, which I'm definitely teaching. Oh, and also, you want to take 490 in the fall, there are 32 seats open. You have all the prereqs you need for that. You've taken, whatchamacallit, you've taken 280 and you've passed it, I hope. You should be ready for 490. And that is a very hands-on. If you want to go into test engineering, or you want to learn more about printed circuit board design and putting ICs on a board and signal integrity issues and some of the analog issues going between them, it's a really good class to take if you want to build anything. That's what I say. Even if you're a power person, it's a good class to take. Yeah, and there are openings, so please fill some of those openings. It's cheaper to use an older process that's established if you don't need the density of 5 nanometers, which is the fab they're building down in Phoenix right now, or 3 nanometers. You'll have, okay, or 3 nanometers, then you're going to use a cheaper process. Micron's using 9 nanometers for their memories because they have to get the capacitors a little bit bigger. 325 is still required. You will have to talk to Dr. Winfrey to figure out when that deadline's coming or when that change is going to happen. Okay, take 490 in the fall. It's a great class. People who've taken it say it was like the class that made them realize what it was to be an engineer and stuff that you're actually going to do as an engineer as opposed to what professors talk about. The final exam is Monday, April, and if you take 490, then I don't have to teach like something else. 325, oh, 325, you have to send an email to Dr. Winfrey and find out when 325 is going to be dropped. I don't know the exact date. And you would have to update your program of study to the new one that has 325 taken out. Winfrey has the details. I don't know. I don't know who's going to follow. Yeah, never mind. The final exam is Monday, April 26th. So that's like the first day of finals. We'll get it over with 3 to 5 p.m. I'll let you bring in 5 note sheets. It'll cover everything we've covered this semester, cumulative. So exam 1 and 2 stuff, the linear systems, the switching networks, Laplace transforms, Bode plots. We've covered a lot. Diode semiconductor physics, MOSFETs, and these BJTs. So go back, the things I would key in on to look for if you have a limited amount of time to study. Go through the practice final exam and the final review. Then look at the exam 1 and 2 reviews, the exam 3 and 4 reviews, any homework solutions for things you're getting stuck on. Then if you're really drilling deep into this, go into the lecture slides and solutions and the reading assignments. It's almost over. You should have a good attitude. Summer's coming. Extra pay because you can work more or something like that. Yeah. This is the first transistor. It was a BJT research device. And this is what we do in research. We don't put things together that are perfect, but we put new ideas together that actually work. Most of my life was in technology development, building things that didn't exist before. So I'm good at trying to figure all that new system stuff out. So this is BJTs. It's an NPN structure. So if you think about this, it literally looks like this. I have an N region, I have a P region, I have another P region. There's also a cousin of this called a PNP, where we just swap those. I have a diode right here. So you could think of this as, well, this is a diode, this is the P side. So P side. And I have another diode over here, and this is the P side. I got another connection right here. So it's like having two diodes back to back with a connection in the middle. We're going to look at some different DC biasing circuits and how they work. You've done a little bit of this in the lab, but we'll go through kind of like the theory of what you did in the lab, and hopefully help you out being a little bit more ready for next week's lab. But Bernard and Pink Eye did a good job going over it. So it's still with amplifiers. Usually we're using BJTs if we want an analog circuit. So our most basic building block of analog is an amplifier. I want to figure out a way to make small signals into big signals. And they do make superior amplifiers to MOSFETs. Just in a lot of circuits, if you're dealing with something like a memory, you're not going to pay extra to have the BJT processing and the CMOS processing, because it's a lot, that it would be a lot of wasted money for a better amplifier when you can build an adequate amplifier using MOSFETs. And we'll learn how to do that in 380. Boy, will you ever learn how to do that in 380. So here is the amplifier schematic we've already looked at. It's got a MOSFET in there. It's got a 3-terminal device in there. It's a transistor. There's a gate, a drain, and a source. The circuits look fairly similar, except for this symbol has changed. It's no longer square. It's got little angles on it. This is an NPN transistor, which is also called a bipolar transistor. Short name for that is BJT, bipolar junction transistor. Either one of those works. The terminal names are going to change because these were named, these were the first transistor they actually built, and they were trying to get something that acted like a good vacuum tube, a solid state vacuum tube that wouldn't burn out as easily. So they named them after the old vacuum tube terminology. I've got a collector, I might as well spell it, collector. Down here I have an emitter, and the collector collects the electrons and the emitter emits the electrons, which means electrons are flowing in this direction, which means electrical current is flowing down from the collector to the emitter. And the other thing I have over here is the base, which is kind of like the gate. So the base is like the gate, the collector's like the drain, and the emitter's like the source. Just replaced it with a different transistor. This is called a common emitter amplifier instead of a common source because the emitter is common. And we'll get to that probably next class. I've never had this luxury of having this much time. There's seniors who claim they've never heard about BJTs. In our curriculum. I go, no, I do it in 280. I go, but I did the whole thing in one day because I ran out of time. Well, we have more time. We'll have enough time to maybe you'll at least remember you did it. This is a MOSFET because this is the one we're familiar with. I have 2 N regions in a P-type substrate, and I modulate. I determine whether current can flow or not by putting a voltage between the gate to source here that will form a channel between these 2 regions. And the channel will be something, it'll be an attraction of negative charge to the gate because of the positive charge there. It's a capacitor. So I build this channel where current can flow. BJTs always kind of dumbfounded me when I was a sophomore. I just did the calculations. Here I've got an N-type region, just like I did in the MOSFET and another N-type region, and I've got a P-type region in between them. But how do I get current to flow? Because there's like 2 back-to-back diodes here. I can't get current to flow backwards through a diode unless I play some little tricks on here. And that was the part that really got to me. I think I'm finally going to be able to, I finally got a good explanation in the slides. And we'll get to that. And 3 terminals. So we've got 2 PN junctions. I've got the base emitter. So going from the base to the emitter, I've got a PN junction. And going from the base to collector, I have another PN junction. So we could look at this and we could say, okay, so the base emitter, base collector, and we're going to say what's going on here. I'm going to give it a name. Region is the word I wanted to write right there. So the base emitter junction could be reverse biased, and the base collector could also be reverse biased. And then I could reverse bias this one and forward bias this one, or I could forward bias this one and reverse bias this one, or I could forward bias both of them. So I've got 4 different regions of operation. A MOSFET had 3. Most badly named regions of operation in the world, and you'll understand that in about a minute. If they're both reverse biased, current can't flow through either diode. So this is called cutoff. Thank goodness. Okay. If I'm just going to declare this at this point, not explain why, because I'll explain why in a minute. If I reverse bias the base emitter and forward bias the base collector, we call this reverse active. And if I forward bias the base emitter and I reverse bias the base collector, this is called active. And this is what we use for amplification. It's like saturation in a, I'm starting this already. It's like saturation in a MOSFET. If I forward bias both junctions, we call that saturation, which is like triode in a MOSFET. I'm sorry. I'm really sorry. I didn't pick these names. This confused me for quite a while when I was first starting out, because we learned both kinds of transistors in school. We spent probably more time on BJTs, and getting the names of the operating regions straight was just beyond me, because if saturation in a MOSFET, well, that use that for amplification. Saturation in a BJT, you use that for digital. They just had to do that with the names. I'm sorry. Where are we at? Oh, good. Somebody's awake. What are the middle 2 regions called? Reverse active and active. I'll have more room to write that in a minute. This is slide 15. 42 slides. Okay. So I made this slide myself because of the relative confusion I have with names. In a MOSFET, if VGS is less than VT, we call that cutoff. That corresponds really well with the cutoff region in the BJT. If we look at, in this curve, we were looking at VDS versus VGS. This is VBE, VCE versus VBE. So except for swapping the names of the terminals, the curves look pretty much the same. The names of the region are different though. The region in MOSFETs where I have amplification is called the active mode, Over here, that's a BJT. Over here in MOSFETs, it's called saturation. So those two terms go together, active and saturation. Notice the slope of the BJTs is much higher. That means I'm going to get higher gain out of a BJT. And if I have higher gain, I'm going to have better frequency response because gain times bandwidth is always a constant. That was 380, but gain times bandwidth is always a constant. If you have steeper slope, you have higher gain, you can have higher gain at a higher frequency. So these are going to be higher frequency devices. When I was at Motorola and I designed an amplifier for 1 gigahertz, we did not use MOSFETs, we used MESFETs, which is a cousin of the JFET, okay. But it's a metal epi semiconductor field effect transistor made out of gallium arsenide. Again, a little bit higher frequency response than we could even get out of BJTs at the time. Okay, triode is what we use for our digital. We use cutoff for digital. We're going to use, over here, we're going to use saturation for digital and cutoff for digital. Active will be our analog. Active will be our analog region. And we can already see that slope is steeper, so if I put a smaller signal in here, I'm going to get an even bigger signal out on the output. Okay. I wrote this slide today too. Remember for PN junctions, this was on your exam, the way we're going to get this thing to work is we need to get most of the depletion width on the P side of the junction. And this is the equation for the depletion width. The equation for the depletion width on the P side, which we want to be big because we want to deplete that P region completely. We need to have ND big. So if I dope the N side more heavily, the depletion width will be bigger on the P side, and that's what we want. So we want N plus, and my Xn is W times Na, the concentration of holes I put in on the P side. If I dope the P side more lightly, then the depletion width, it'll be bigger on the P side. We want that. That's the same thing. So we're going to put P minus, which means P minus means it's a lightly doped region, and N plus is a more heavily doped region. Which N side to dope if there is two? We'll get to that. One of them we're going to dope them a little bit differently because with a MOSFET, the drain and the source are completely symmetrical. They're the same. With an NPN transistor, there is one side we deliberately make the emitter. It's going to be more heavily doped than the collector, and we'll get to that in like the next slide. So ask me again after the next slide if I don't get to that. So what we're going to do here, we want to put this in the active region, and this is what I'm going to use for amplification. So this base emitter junction is forward biased. Lots of current can go through there. The base collector junction is reverse biased. So you're expecting no current to flow through a reverse biased diode. A couple of things we can do to make that happen. First of all, I'm going to force a lot. I'm going to make this like relatively forward, pretty forward biased here. And then it's a diode, and we put this at N plus, we put this at P minus. So most of the depletion region is going on the P side and just a little bit over here. Remember that depletion region is a region on the P side that gets charged negatively. So I get a lot of negative charge across here, even though it's a forward bias junction. And the next thing I do, since I'm reverse biasing this side, it's actually going to have a wider depletion region, and I get the depletion region from this junction all the way back over in here, so that this whole piece region becomes depletion region. And then I can push current through there. It's like an N at that point. So tricks people use to design this is they make the width of the P region really small. We want a thin base so that the depletion region on the collector base side, which is going to be the wider one, will extend deep into the base, and the smaller depletion region on the base collector side will extend in, and you have depletion region all the way across. And then current can freely flow. Let me get rid of all my electrons on here. So we get rid of the electrons. Now, when we think about this, I've got electrons ejected into this PN junction. This is physics current. This is actual electrons moving, not electrical engineering current. So these electrons get injected into here. They freely flow across the forward bias junction. Some of them will actually flow into the base. And then because I've got a depletion region across this really thin base, some of them will end up in the collector because I've got that whole region across there. And that's the reason why we dope it the way we do. Now, which means, yeah, and if electrons are flowing to the right, electrical currents flowing to the left. And that's why these electrical currents like IC and IE are shown flowing in the opposite direction as the electron flow. Okay, so we have to, for active mode, we're going to forward bias this one, the base emitter junction, and we're going to reverse bias this one. So forward biased on this one means the P voltage has got to be higher than the N voltage. So VB has to be greater than VE. And if I reverse bias the other one, that's going to give me VB has to be less than VC. And then our little transitive property is going to tell us that VC must be greater than VE. Okay, so that is active mode. And mostly we're not going to talk about, the only time you'll see the BJTs used in digital circuits, you see them on printed circuit boards in something called a series pass transistor. It's basically you're using an Arduino to turn on a large amount of current to a motor. You might use a BJT there, but mostly they're used for amplifiers, both in integrated circuits and if you need a single transistor amplifier on a board. Okay, active mode is analog. Now, when we actually build these things, this is kind of like what they show in the book, and it's easier to think about it this way. But when we build it, we're building the circuit in an N-type substrate. We'll put the collector contact to to the substrate. Build a P well on top of that, put a base contact to the P well, and then build an N well inside of that to build the emitter contact. This is more like what it looks like when I do the fabrication. Who does analog? Nobody does analog fabrication in onsemi, they do analog fabrication. I don't think they actually make the things down in the valley though. Okay, so there are, thank goodness. Are the wells actually centered? Let me look at that. There will be like one transistor here. Wait, well, no, oh, thank goodness. There'll be one transistor here. They may not be complete. This one's probably centered within the P region, but there'll be other transistors next to it. Yeah, I would say probably. Yeah, I don't know what modern BJT processing looks like. Nobody's doing that in Arizona. My guess would be yes. And in fact, when I was in grad school and talking about processing a lot more, nobody was talking about BJTs. So I don't think I can honestly answer that question. People who do this are people like TI and onsemi and Analog, and which bought Linear, and Maxim. They're all have offices in Arizona. So there's three main equations when we're dealing with active mode. The first one, and this is a definition, usually in textbooks they use beta, but if you're looking at a data sheet for a transistor, they use HFE, which comes from two-port network terminology. It's basically the forward current gain. And this beta is it's a parameter that's measured on the device, and it's going to equal the ratio of IC to IB. So it's the current gain of the device. Now, if you actually read a data sheet for a NPN transistor, one of the things you're going to find is the spec on there for beta will look something like beta, guaranteed greater than 20. Typical value, no answer. Maximum value, 200. So it varies from like a factor of 10, and all the hand calculations you do are based on this, you think you know beta. You don't know beta. And I've actually seen people go and sort transistors out of a bin to find a high beta one, so their circuit will work. It's very poorly controlled. But it is the ratio of IC and IB, and we'll pretend like we know it for this class. You can measure beta, is usually the most efficient thing to do. This current, the collector current, is going to equal this constant IS. It's just like IS for a MOSFET. It's a constant of the device. It's something you're going to look up on the data sheet. That's a little bit more reliable. Times e to the VBE over VT. And VT is still KT over Q, which is 25 to 25.9 millivolts, depending upon what you call room temperature, at room temperature. So that's a constant. And IE, we can use KCL. The current going into this device is the collector current and the base current. So IB plus IC has to equal the current going out, which is IE. So some quick calculations you can do. You know beta, you've actually measured it for this device. You know the collector current, and you know VBE. You want to figure out what is IB. So I use this equation right here. IB is beta IC. And I do that calculation. This is number 7. That comes out to be 12.5 microamps. IB is usually a lot smaller than IC or IE. And IC and IE usually about equal each other. If I want to find IE, I can just use this equation right here. It will equal
IC plus IB, and I add those two together, and I get 1.0125 milliamps. And then the last thing is to find IS. I could take this equation right here and solve it for IS. It would be I for E to the VBE over VT. And then I would throw that into the equation. I would throw that and do the calculation. I could calculate IS, and IS is 93.6 attoamps. I usually spell out the atto because I don't use it very often. An attoamp is 10 to the minus 18th amps. An attoamp is about 10 electrons per second. A pretty small current, and it's just modeling the leakage current of the device. So pretty good leakage current because we got two back-to-back diodes. They're not going to conduct at all if I turn them both off. Okay, so I got another condition here. Beta is 120. I know what IB is. I know what IS is. So I know the data sheet stuff right here is beta and IS. I want to figure out what IC is. Well, IC is, oh wait, I did that wrong. I wrote that equation wrong. Sorry. This one should have been, let me change colors. This one should have been IC over beta. Our IC is beta IB. That's going to be much bigger than the 50 microamps. It's just 120 times 50 micro. Once you get the equations, they're not hard to do. I say that now. IC is 6 milliamps. We can use this equation right here. IE is just IC plus IB. Since we know the other two currents, we can figure out the third. So 6 milliamps plus 50 microamps is 6.05 milliamps. IE really approximately equals IC. And if we want to solve this equation for VBE, that would be IC over IS, and then we'd have to take the natural logarithm of that and multiply the whole thing by VT. And we could solve for VBE that way. And it comes out to be, it's usually about 0.7 of a volt, 736 volts. Okay. So this is how you do these DC calculations. Always go back, like on your note sheet or wherever the note sheet you're using to do your homework. Write those three equations down right there. You can usually get enough information out of them and some basic circuit design to figure it out. Another useful equation here is this thing called alpha. Sometimes I don't know IB and I only know IE, so I have to solve for IC. This thing, the ratio, and this is just algebra, alpha is IC over IE. This is just beta over beta plus 1. So if I know beta is 80, my alpha would be 80 over 81. If beta was 200, my alpha would be 200 over 201. As alpha gets bigger, as beta gets bigger, alpha gets closer and closer to 1, and it's always nearly equal to 1. If you need to get beta from alpha, you could just do a bunch of algebra here, solve for beta, and beta would equal alpha over alpha minus 1. So that's another fourth equation that might be fairly useful too. The three on the last slide and this one. Yeah, And the rest of that you should be able to figure out how to do. 22. Okay, if you apply KCL to this, currents going in equal currents going out. IB plus IC are going in, and IE is going out. We've already used that equation right there. We've got this equation. We've got alpha, and what was the other one? IC equals IS E to the VBE over VT. So those are the four big equations right there. So given different conditions between those four equations, you should be able to find everything you need. Let's just do part B. The rest are amazingly similar. So we've got IC, we've measured that, we've measured IB. We want to figure out what beta really is for that transistor and not what the data sheet says. So my beta is going to be IC over IB. You can simulate these two. Well, simulating doesn't help you with your particular transistor. 1 milliamp over 8 microamps. And what does that come out to be? Number 9. Beta is 125. So we got a pretty good transistor here. Let's keep this one. What else do we want to do? We want to find alpha. Well, once we get beta, alpha is beta over beta plus 1. So this is pretty darn close to 1. It's 0.992. 99.2% of the emitter current actually makes it through to the collector. And then we can find IE. Well, we've got IC and we've got IB. So we just use this equation, IE equals IC plus IB. I froze. IC plus IB, which is 1 milliamp plus 8 microamps, is 1.08 milliamps. They'll be back shortly. Wow. I'm frozen.